One of the techniques that lets you simplify a circuit is to use the Thevenin Theorem or Norton Theorem, and we go through both of them quickly. The Thevenin Theorem says that if you have a circuit, a linear circuit first of all, so that's very important, it's only applicable to linear circuits, with any combination of linear components here. So let's say an inductor here, a resistor there, let's say a current source here, and let's just maybe add a resistor here, a dependent current source, let's just use one here, put a resistor here, and the voltage source here. So this is a fairly complicated circuit, right? And what we have is this circuit connected to some other circuit that is of interest to me. So let's just represent that other circuit with a resistor for now. And I'm more interested only in how the voltages across this resistor change in different conditions and all that. I'm not really too concerned about what's going on in the circuit to the left. So what I want to do is that I want to make my life easier and come up with a simplified circuit that will still keep my KVLs and KCLs intact for whatever that is happening from this point onward. But I don't want to be concerned with what is going on in those loops and at those nodes. So the Thevenin theorem, so Thevenin circuit, Thevenin equivalent circuit, of this left side, everything to the left of it, is simply an impedance. We call it the Thevenin impedance, and a voltage source. So basically, I reduced everything that I had to the left of that circuit. It's independent sources, dependent sources, all sorts of linear components. I reduced all of that to just one voltage source and one impedance. And you can prove that this actually captures all the behavior of that circuit. To the left, you replace all of that with one source, one impedance, and basically make your life much, much easier as you go through the analysis of the circuit. Now the question is that how do I calculate the values for the Thevenin impedance and source, or how do I maybe come up with a measurement technique to figure them out. The Thevenin voltage is easy. So what you do is that you open the circuit from wherever that you want the equivalent circuit from that point before that point, and you measure that open circuit, right? Open circuit voltage. So basically I take the load, I take the remainder of the circuit away from what I had here, I measure this open circuit voltage, and V Thevenin is simply equal to V open circuit. So that's easy, right? So you can easily find the open circuit voltage. It's measurable, but you can also do a calculation and quickly find it. Z Thevenin takes a little bit of work. So there are two ways of calculating Z Thevenin. There is one that you're familiar with from electric circuits, and in this case, in this method, what you did is that you went ahead and short-circuited that port. And now that you have short-circuited that port, there is a current flowing here, and you measure or calculate that short circuit. So measure or calculate I short circuit. Once you have that, Z Thevenin is V open circuit divided by I short circuit. So this is the method that we have learned before, we used before. So you do a calculation or measurement of the open circuit voltage, you do a calculation or measurement of the short circuit current, and you calculate Z Thevenin from that value. There is a different way of doing the same thing, finding the equivalent impedance of whatever that is behind that port, that we actually use more often in this course because we're dealing with nonlinear circuits, and things are basically not that easy. If you open circuit and short circuit different nodes arbitrarily, you may actually put devices in operating conditions that are not desirable. Even confusing those things may create some challenges later on. So we have a slightly different way doing the same thing, but a different method for doing the calculation of the Z Thevenin. Both are correct. If you know one better than the other, if you're comfortable with one, you can just do it. But the other method that I'm going to talk about is the method that we use to calculate the equivalent impedance of all sorts of circuits in the future. And we can use it for the to find the Thevenin or Norton equivalent circuits as well. I'm going to talk about Norton equivalent circuit, and then I'll do an example. For Norton equivalent circuit, you simplify that left side of that complicated circuit, what we had here at the top, you simplify it to just a current source, I Norton, in parallel with an impedance. So let's call it Z Norton. And then all of the complexity that you had on the left is reduced to just one current source and one impedance. Now, how do we know the value of I Norton? Actually, if you do these calculations here, it turns out that I Norton is your short circuit current. So you short circuit those two ports, measure the current that goes through the, let's say, wire that you used or calculated, and I Norton is your short circuit current. What is Z Norton? As it turns out, Z Norton is equal to Z Thevenin, right? It's the same thing. You just, the way that you calculated the Thevenin equivalent resistance, you use it to calculate Z Norton. So basically, if you have VOC and ISC, you divide them to figure out what Z Norton is, or you use this other technique that I'm going to talk about in a second. Now, you can use either one of these two circuits to represent a complex linear circuit, and depending on whether you're dealing with, let's say, current sources on the right side or voltage sources on the right side, you may choose one of these two, and both of them are very, very similar. One quick mental exercise for you sitting at home is to show me that these Thevenin and Norton equivalents of the same circuit will actually give you the same IV characteristic here, and that shouldn't be too difficult. So for example, if you connect them to any circuit, and they must be the same, they're the equivalent circuits of the same circuit, you will basically see the same thing. Let's say in the simplest case, you will measure the same VOC for both of these circuits and the same I short circuit for both of these circuits. And it should be obvious, but spend a little bit of time on it and make sure that you do this mental exercise. Now, what we do is that, as I said, we have another technique that we use to calculate the equivalent impedance that we have for both Norton and Thevenin circuits. What I do in this case is that I take this circuit, I zero all the independent sources in that circuit. So if I want to zero a current source, zero current means an open circuit. It means that I take this current source and I basically remove it from my circuit. And I have an independent voltage source here. If I want to zero a voltage source, I take out this voltage source but replace it with a short circuit. So I do that. I keep all the dependent voltage or current sources that I may have in that circuit. So all the independent ones are gone. All the dependent ones stay. Then I attach a test source to the port here. So let's just call this Vx. You can use a current source. It's your source. You can use a voltage source or a current source, whichever that is more comfortable in different circuits. Sometimes it might be easier to use a current source. And I attach a test source. Some people use the value of 1 for this test source. I just say, use Vx. And then you calculate Ix. And then you can show that Z Thevenin, or I'm just going to call it Z equivalent. Zeq is the ratio of Vx over Ix. And this Zeq, you can use it as Z Thevenin in the Thevenin equivalent circuit, or Z Norton in the Norton equivalent circuit. And as we will see later on, we actually use this a lot, this kind of a calculation a lot, to figure out what is the input impedance of a circuit or what is the output impedance of a circuit. And we replace a very complex network potentially with just one resistor as, let's say, the output resistance or input resistance of the next stage. So this is a technique that we are going to use very often. And this is how we do it. You attach a test source to that port, let's say voltage source, you measure the current that goes into the circuit, and from that point onwards, Vx over Ix is your equivalent impedance. Very, very important point, to zero all the independent sources, but keep the dependent sources in your circuit. So let's just go through one example. And this method here, you have seen it in your circuit theory, right? So I'm not going to do that or use that here. The example I'm going to solve is that I'm going to use the method that I just mentioned here. It may be a little bit longer in this particular case than the calculation of the short circuit or short circuit current and dividing VOC to ISC, but just an example or a practice for the technique that we're going to use in future. Let's just try this. So this is the circuit that I'm dealing with. I have V in here. Let's just call this voltage V pi. This is a resistor R pi. I have a current source, dependent current source here, whose value is GMV pi. And I have two resistors here. Let's just call this guy RO and RL. And let's say the final goal of the problem is to find out V out, right? And what I want to do now is to find the equivalent circuit for this portion of the network, right? So what is the Thevenin equivalent circuit for that portion of the network? I want to figure that out and use that to find out what the output voltage may be. I'm going to solve this for a Thevenin equivalent circuit. You can go through the solution for a Norton equivalent circuit at home and just make sure that you're comfortable with both of them just in case needed, right? So the first thing I want to do is that I'm going to calculate the open circuit voltage here. So I'm going to take this part of the circuit away, so take it out, keep the output node open, and calculate the output voltage. So quickly drawing it is going to be like this. V in. I'm not going to label the values here. Well, actually, let's just do that. GMV pi. So VOC is from ground to here. So this is ground, and this is VOC or V Thevenin. So if I want to calculate VOC, I can see that in this loop here, I have current GMV pi going through RO. It goes from ground up, so the voltage here should be more negative than the voltage at the bottom of that node. So I can see right away that VOC is minus GMV pi RO. Okay? And this is actually how I'm going to solve the circuits, and you will see throughout the course that I usually start from whatever that I'm interested in, write the equations there, and then see what other equations I need or what are the other variables I need to figure out before I can solve that equation. So I write the equation at the output. I now notice that I don't know V pi, so I know we'll go and find an equation that gives me V pi as a function of V in and all that, right? So at the output I have that. So GMV pi is the current. The current is flowing this way, so the voltage here will be more negative than ground. The current goes from ground up, so VOC is going to be minus GMV pi times RO. Okay? Now, as I said, I have this equation. I know GM, I know RO, I don't know V pi. What else can give me V pi? I notice that in this loop here, I can easily see that V in and V pi are equal. Or if I go and write a KVL, a formal KVL in there, it says minus V in plus V pi is 0. So therefore Vin and V pi are equal, and I can see that VOC is minus GM RO Vin. So that's the value of my open circuit voltage at the output. Now the second part of the question, or the second part of the problem, is to find the equivalent Thevenin resistance. In this case, it would have actually been easier if I calculated the short circuit current at the output. You can actually do that quickly and see what happens. If I short circuit the output to ground, you basically bypass RO, all of GM V pi goes through that short circuit, and you can calculate, you already have V pi, you can calculate the short circuit current very quickly. I'm going to use the method that I just talked about in the, let's say past 5 minutes to calculate the Thevenin. In this case, it's actually not it may not be that much simpler. So, to calculate the short circuit, the Thevenin equivalent resistance, I go and redraw my circuit, but this time I zero all the independent sources. So I had V in at the input that I need to zero now, so V in is replaced with a short circuit. If I had a current source, it would have been replaced with a open circuit. Now, on the right side of that gap, I had a dependent current source. So remember, dependent current sources stay, whose value is GM V pi. Then I have my RO here. And now I want to use a test source. So I connect my test source to this port. Remember, I want to find the equivalent Z Thevenin to the left of that connector. I attach my test source here and calculate this IX. Okay? So in this case, I can see that IX is going to give me two current components, one going down RO and one going to that voltage source. Controlled current source. And the other thing I noticed right away here is that in this circuit I noticed that V pi is actually 0. Once I short circuit the input circuit, the input voltage source here, V pi will be 0. Both sides of this R pi are connected to each other. So that makes my life easier. What that now means is that GM V pi is 0. So that dependent current source that I had in my circuit turned out to have a 0 value. But that's after I solved the circuit. I don't keep it, I don't take it out of my circuit. It just turned out to have a 0 value in this circuit. And now that I have basically this left side of the circuit is basically nothing. There is no current going there. My life is easy. This current is therefore 0. The only current that goes or is drawn from Vx is going to be the current that goes through RO. I already know the voltage drop across RO, so IX is simply Vx over RO. And if I want to calculate my Thevenin equivalent circuit, it's going to be Vx over Ix, which in this case actually turns out to be simply RO. All right? And now I have my equivalent voltage source. I have my Thevenin impedance. I can reduce all of that circuit with a much more simpler circuit. Do the same thing for the Norton equivalent circuit. Find the Norton equivalent circuit for this network. And also try to calculate the equivalent impedance using the method that you know from electric circuits. So go and, you have the open circuit voltage, find out the short circuit current, and divide the two to each other to see if you get the same value as we did here. You must. Okay? Now, so just to sum it up, the Thevenin and Norton equivalent circuits, they make your life much easier in terms of, giving you insight on how a circuit behaves. And we use them a lot. In electronics, we use them a lot to simplify the circuits. There are just one very, very important condition, that Norton and Thevenin equivalent circuits can only be created for linear circuits. So if you have any nonlinear components on the left side in, whatever that you're trying to simplify, you cannot use a Norton or Thevenin equivalent circuit for that component, for that portion of the circuit. You may, however, be able to take that component out, reconfigure the network a little bit, and come up with a Norton or Thevenin equivalent circuit for the linear portion of the circuit, as long as it stays connected and you get one port for that part of the circuit. Now, the last circuit theorem that or technique that we want to quickly overview here is superposition. Again, it's a technique that you use to analyze linear circuits, and superposition basically means that if you have two sources that are applied at the same time to the circuit, two independent sources from each other, what you do is that you look at the output due to one of them while the other one is taken out, calculate the output, then insert the second one, take the first one out, calculate the output, and the true output when both of them are attached to the circuit is the sum of the two. So if you go back to what superposition or a linear system means, for a linear system, f of a plus b is f of a plus f of b. So this is basically a simplification for the definition of a linear circuit. But for a linear circuit, if you have a and b as the inputs, f of a plus b is f of a plus f of b. And that's what superposition is, right? So it says that if you have a voltage source and a current source that are driving a linear circuit, you can look at the output, the combined output as being the output from the voltage source measured independently and the output from the current source measured independently and then added up together. Superposition makes our lives easier. In many cases, your KVLs and KCLs become a bit more, let's say, manageable if you use superposition. The only condition here is that you have to absolutely have a linear circuit. You cannot really use superposition whenever you have a nonlinear component in your circuit. And just try to think why, right? So think about a nonlinear function. Let's say f of x is x squared. It's just a square function, not very strongly nonlinear. And f of 1 and f of 1 plus 1 are not f of 1 plus f of 1. So f of 1 is 1, f of 1 plus 1 is 4, because x squared is 4. And f of 1 plus f of 1 is just 2. So this is a very, very simple example. You only use superposition for linear circuits. You should have seen this in your electric circuit theory. If you need a refresher, just go and do a quick practice on that. And these techniques that I talked about are the tools that we need all the time in electronic circuits. You use KVLs and KCLs all the time. You use superposition from time to time. Norton and Thevenin equivalent circuits are used all the time in electronic circuit analysis. One other technique that we use a shorthand to analyze more complicated circuits is voltage division and current division rules. So for voltage division rule, and again, these are things that you should have seen before. If not, just do a quick check for yourself and make sure that you understand how these things happen. So if you have two resistors in series, let's just call this R1 and R2. I just cite the output here. And you are interested in figuring out the voltage at the node between them, as long as you do not draw any current here. So this current is 0. Basically, open circuit measurement of that voltage. You can show that V out is equal to R1 over R1 plus R2 V, right? And if you have two resistors in parallel, you can show that the current actually divides between the two in a similar way. The voltage drop across this guy is proportional to this resistor. The voltage drop across this guy is going to be actually R2 over R2 plus R1 times V in. And this is called the voltage division. You can see that I divide the input voltage by a ratio. I actually use this circuit a lot in electronics to create whatever voltage that I need from a higher voltage. So let's say you have a 10 volt power supply, but you need a 2 volt DC voltage to bias your circuit. You use two resistors, let's say 2 kilo ohm and 8 kilo ohm, to create a 2-volt signal from the 10-volt input. So again, a voltage divider or a current divider is, if you see a circuit like that, as long as you do not draw any current here, that's very important. As long as you do not draw any current from that node between the two resistors, you can figure out the voltage there fairly quickly from this ratio. And this will be it. So again, I highly recommend you to go back and do a few exercises on your own. There are some suggested problems from the textbook that you can use. If there are any questions regarding this, we can cover some in the live lecture, maybe a couple of problems we solved using these techniques if needed. And that will be it for this lecture, this session. For the next session, we're going to talk about the simplest of all nonlinear devices in this course, a diode.